Welcome, ladies and gentlemen. At this time, I ask that you take a look at your Bellwork today. We're going to sketch the solution curve that contains 0, 2, given the slope field of a differential equation. We can do this simply by estimating. We can pretend that we're dropping our leaf in the proverbial stream and we're watching where these direction arrows, the current takes that leaf. And so where's our initial point? Well, 0, 2 is right here. If we were to drop our leaf in the stream, where would the current take it? Well, it looks like we're going to follow the direction of the nearest mini-tangent line segment, wherever that might be, and see where we go with the solution curve. So I'm thinking I'd be going down here, and then maybe over, parallel to the nearest thing. Oh, up, yeah. And then looks like it kind of goes that way, doesn't it? If I wanted to go in the same, the reverse direction, it looks kind of like something like that. That is just an estimate. You're doing it visually, you're doing it graphically, right? And it may or may not be close to the actual solution curve. We don't have enough given information if we're just given a picture, a visual representation of the differential equation and slope field that it produces. Now let's go ahead and suppose that 2x minus y is my differential equation dy dx. And let's start at that same initial condition, 0, 2, but use Euler's method, our new method for approximating function values, right, by using little steps, delta x steps, and the instantaneous rate of change at the latest known point. All right, so we'll start out at our known point, 0, 2. We'll calculate dy dx, my instantaneous rate of change there, and then multiply that over my small delta x step to anticipate my next point. We'll then reiterate the process until we get all the way to our our wanted x value is x equals 2, and we're starting at x equals 0 with the delta x step size of 0.5, so we'll be taking 4 steps. Are we good? All right, let's do it. So what does dy dx equal? Dy dx would equal 2 times 0 minus 2 is, I don't need all that. So that would equal negative 2. All right, negative 2 times my delta x step of 0.5. So my anticipated change in the function y value, dy, my estimate for that change is given by negative 2 times 0.5. So half of negative 2 is negative 1. So is it negative 1? I'm going to now apply that to which coordinate? I'm going to apply that to my y coordinate. My anticipated change in the y coordinate after one step is 2 minus 1 is 1. Meanwhile, I've stepped over a delta x, right, step of 0.5. So from 0 to 0.5 is 0.5. So raise your hand if you had 0.5, 1 is your first step. And then we just reiterate the process. Next step. Dy dx 2 times 0.5 minus 1 equals 2 times a half is 1 minus 1 is 0 is my anticipated change, instantaneous rate of change at that point. Multiplied by my step of 0.5 is 0 times 0.5. I anticipate a change in y value of 0 units as I go to my next step. So it looks like we've gone from 1 plus 0 is 1 still, and another 0.5 units delta x horizontal step puts me at 1, 1. Is that right? So 1, 1. Awesome. We're closer, so let's go ahead and continue the party. Differential equation dy dx gives us an instantaneous rate of change at 1, 1 of 2 times 1 minus 1 is 2 times 1 is 2 minus 1 is 1. Are you getting 1 times my delta x step of 0.5? So I get an anticipated dy change of 1 times 0.5 is 0.5. To my y unit, last step. So 1 plus 0.5 is 1.5. My delta x increases my x value by 0.5, so 1 plus 0.5 is 1.5. Raise your hand if you had 1.5, 1.5. Almost there. All right. And we're on the home stretch. So let's go ahead and finish this out. Instantaneous rate of change at 1.5, 1.5 is 2 times 1.5 minus 1.5. That is 2 times contain 0.75 minus 1, negative 0.75? Is that what you guys got? Negative 0.75? No? So 2 times 1.5 is 3. Minus 1.5 is 1.5. Is that better? 1.5? Yay! Times my delta x 7.5. So what's half of that? There's my 0.75. So I've got 1.5 times 0.5 is 0.75. And finally, at long last, I anticipate my final y coordinate after stepping over, right? After stepping over 1, 2, 3, 4 steps all the way to x equals 2, we anticipate a y value of 1.5 plus 0.75 is 2.25. Yes, 2.25. Awesome. So what does this mean for us? At long last, it means our anticipated function value is 2.25. Awesome. Woo. What questions are you guys having about Euler's method? So Euler's method is a topic that's new and specific to the BC curriculum, so you'll definitely see Euler's method somewhere. I'm not sure if it'll show up on multiple choice or free response or both, right? We don't know what the test is going to look like this year. I did just download a new practice test that was released from the 2016 administration last year for BC, and so we'll be able to do practice problems like this, and you'll get a full-length practice test just like we did in AB. You'll get 2 full-length practice tests for the BC to prepare for the exam, and we'll see kind of to what extent Euler's method then is incorporated in those 2 most recent released practice exams. All right, so let's go ahead and see what the computer did. So the computer went ahead and took our 0.5 steps and generated this picture, and we anticipated 2.25. Is that what the computer did? Well, if I visually look at my y coordinate, that looks about like 2.25, so not too shabby, right? So we did pretty well. All right, I'm going to go ahead and pause the recording. We'll take care of our OTL. This is the other one, though. There we go. So we're going to call this OTL2B, and it's our integration review, and it's out of 25. Okay, so at this time I ask that you go ahead and make sure your name is on that. All right, ladies and gentlemen, so today we're going to look at our exponential, right, growth and decay. And while we're familiar with, right, our applications that involve rate of change that's proportional to the amount of a quantity present, we use that kind of exponential law of change when we're dealing with our compounding interest continuously in our APERT formula from long ago, our radioactive decay from chemistry, right, and so on and so forth. But we're going to extend it today to include relationships that aren't just proportional to the quantity present and not just use the APERT. We're going to look at a new type of model today that is better suited to real-world phenomena. All right, but first, let's go ahead and recall our basic law of exponential change. Suppose the rate of change in a quantity with respect to time t is directly proportional to the amount y of the quantity itself, with constant proportionality k. What? Suppose the rate of change in a quantity, so there's my derivative rate of change. Let's translate that into a differential equation. So my rate of change in a quantity with respect to time t, so there's my independent variable, we can translate that into a differential term. So the rate of change in a quantity with respect to time t, so that would be dy dt, is, there's my verb, so there's my equal sign, directly proportional to, that means multiplying, right, constant k times the amount y of the quantity itself. So directly proportional to the amount of the quantity itself. So there's my basic, right, my basic differential equation when the rate of change in a quantity, right, depends on the amount of the quantity itself. Can we solve this and get the generalized solution to this exponential differential equation? Well, it's not the exponential differential equation, rather, it's an exponential solution. This is the law of exponential change. Absolutely, and we're going to do that because you'll still see this, right, in your BC curriculum. So let's go ahead and solve and find the general solution, right, the general solution without numbers but just with constants. So what would we do? Well, we separate the variables. We divide over that y and multiply over the dt. So we get dy over y equals k times dt. Now we'll go ahead and integrate both sides. On the left, integrating with respect to y yields natural log of absolute value of y. And that's equal to integrating the right. Remember, k is just a constant, right? That's my constant proportionality. So the right-hand side integrates to kt plus c. Recall from AB, we'll include our constant integration on the independent variable side. And we saw that this was a rate of change in a quantity with respect to time. That form t is my independent variable. All right, so what do we get for the general solution? Well, we want to solve for y. So let's go ahead and solve that for y. How do we undo the natural log, right? How do you undo an ln? Kobe?
Put both sides, or put e to the both sides.
Absolutely, right? We exponentiate e to the. So if natural log of absolute value of y equals kt plus c, then absolute value of y must be given by e to the kt plus c. So we exponentiate and rewrite using our definition of natural log. All right, now we'll go ahead and utilize our properties of exponents and break up that sum in an exponent as a product of power terms, each with the same base. And so recall from our exponent rules, if we did x cubed times x to the 7th, we get x to the 3 plus 7. Well, we can rewrite this right-hand side then as e to the c times e to the kt. Now we'll go ahead and apply my absolute value bars. Recall that absolute value bars, right, are going to return the opposite of the quantity if the quantity inside is positive. Absolute value bars will return the same thing as the quantity if the inside quantity is positive. So we're going to go ahead and get rid of the bars by considering the positive and negative, e to the c times e to the kt. And our base e is a constant Euler's number, c is a constant unknown, and this plus and minus just means all together. We could consider this to be our constant a, which we'll call the initial value. A can be determined using a given condition. Y equals a times e to the kt. Here's my general form. Solution to the differential equation dy dt equals k times y. So this is a famous differential equation and famous solution. Notice how this is your APERT formula, right? Where the amount A in your bank account for continuously compounded interest is given by your principal, P times e to the RT, where now R is your interest rate as a decimal. K here is your constant proportionality. Oftentimes we'll see that as y equals y naught times e to the kt. A lot of times you'll see it, you've already seen that as your APERT formula. All these are the same thing. And so when you see the rate of change in a quantity is directly proportional to the quantity itself, you're authorized to jump right to one of these generalized solutions and plug in initial conditions to determine the missing constants if given. Your first half of your OTL deals with this type of exponential change. So you'll be able to utilize this differential equation and or these generalized solutions to determine particular solutions and answer real-life questions. We're not going to spend today's class period going over the same exponential formula. You've seen it now 3 years, right? If we count our chemistry applications as well. So you've seen this for 3 years. Instead, what we're going to do is consider what happens then. Oh, we just did the generalized solution. Yes, we're ahead of the game. Instead, right, we're going to go ahead and look at some more real-world applications. So our exponential growth and decay, we've seen this, right, in the context of population, right, biology, nuclear chain reactions, computer processing speed, radioactive isotopes. Yes, carbon dating. How old is old? Business and finance with our APERT virus infection. But notice how our exponential growth, right? Our exponential growth takes a while to get rolling, but if you consider these three functions, the red, a linear function, blue, a cubic function, oh, that grows faster than the exponential up until a point, but as you look for the farther and farther right, who wins out? Well, our exponential function is going to win out in long-term growth, right, hands down. You can see that it grows much more quickly as you get here past x equals 10, 11, and so on and so forth. Given that an exponential function continues to increase at an increasing rate, typically these only are going to model real-world phenomena up to a point. Then we're going to, right, we can't sustain this type of growth forever in the real world. And so what happens? Well, then we'll go ahead and switch our model. So the first half of your OTL, if we see that words grows at a rate proportional to the quantity present, or my quantity grows continuously with constant of proportionality k, or 0.5, and so on and so forth, then we're talking about our general form dy dt equals k times y with generalized solution y equals y naught times e to the kt. I'm getting ahead of myself. This is a good reminder for me too. So like the first half of your OTL all includes this type of relationship and growth. But I'm more excited about the real world, right, where we've got exponential growth, definitely can model, right, can model population growth under ideal conditions, certainly up to a point. But oftentimes there's some sort of limiting factor, like space, or nutrients, right, food, predators, and so on and so forth. And so more often in the real world, we have model that exhibits exponential-like growth up to a point, but then that rate of growth or change in the quantity levels off, right, and approaches some value. So this is what we're going to call logistic growth here in blue, and it's going to be the focus of our activity and investigation today. The basic differential equation that yields an exponential solution curve is dn dt equals r times n. That should look familiar. How come? Well, that sure looks like dy dt equals k times y, right? Bless you. Where my dependent variable is the y, in this case it's the n, right? That's my dependent variable. Well, the same thing, right? There's still that same term in my logistic differential equation. See that r times n, right? So there's that exponential quantity, the amount present influences the rate of change, and yet there's some limiting factor as well. And so it's also proportional to the difference between that limiting factor, right, and the amount present. And that's going to influence the rate of change in my given quantity. So it's exponential growth here up to some point, and then we see that growth level off as time continues to go on. You can also see that written as r times n times the quantity 1 minus n over k. Here they just combine that fraction, k over k is 1 minus n over k. But we're going to use what your textbook uses. So your textbook uses m minus p, right? So we've got the rate of change in a quantity. In this case, we'll let p represent p for population, is directly proportional to the quantity itself times the difference between some value m and the amount of the quantity. So here we've got two, right, influences on the rate of growth of my original quantity p, and that's what we're going to look at. For our purposes, we're going to let k and m be positive constants, and so that'll make a difference when you're looking at your activity today. So we're going to suppose that this is in the context of modeling real-world phenomena. We'll let p you can think of as population, t we'll think of with respect to time to keep it in context, and then k and m are both positive constants, and that's going to be a great kickoff point. All right, so I don't want to say too much. I'm pretty excited. I don't know if you guys can tell, but we're going to investigate the logistic differential equation today. I picked out activity stamps, so we're going to include 9, 12D, 15, And a little bit of a stretcher is number 17. But I'm confident that working together, you guys are going to be able to do that. There's more than one way to arrive at the final correct answer, but it is a nice little shot of algebra there. So what I'm going to do is go ahead and turn off the smart board. We're going to switch into our brand new activity groups, and we're going to get started. I have the key that I'll go ahead and scan into, so that I'll get that up on Moodle as a PDF, but it's not up there right now. Okay, without further ado, let's switch into our groups and I'll file it. Sophia?
So for the equation,
Okay, ladies and gentlemen, let's go ahead and take a look then at our general form for the solution to a logistic differential equation. And so we saw that if we had the rate of change in my population was directly proportional to the population itself and the difference between the population and that limiting value, that carrying capacity m, then we could get the general solution, right, by solving for p, and we had to utilize the technique of partial fractions. So we got dot, 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 lots of fun, all the way to a generalized form. Population P then was given by what? M, my carrying capacity, over quantity 1 plus A times e to the opposite of K times M to the T, where A could be determined using a given condition, just like we saw for A in the past. All right. The activity key shows my work in solving the specific one when K is 0.005 and my limiting carrying capacity was 100 individuals. What you're going to do then for closure is go ahead and fill in my chart. And so here we've got a differential equation for exponential model versus logistic model. And then the general solution for exponential model versus logistic model. And so this is kind of the AB, right? Sort of did the exponential model, and that's how we started today's class period. By the end of today's class period, we got the logistic. Please use constants, right? Don't need any numbers here. Okay, so for an exponential model, what's our original differential equation given by? Right? What's our differential equation given by? Grace?
dy over dt equals ay.
Good, that's perfect. So that's when the rate of change in my quantity y is directly proportional to the amount of my quantity itself. Good. What does my logistic model look like? Emily?
dp over dt equals k times d times quantity m.
Good. Here, I still have the rate of change in my quantity p directly proportional to the amount of that quantity p, but also another factor where I take into account the difference between the current population and this carrying capacity, that value of m. Oh my goodness gracious. Our general solution then for the left exponential model goes to what, Sophia? And I'll use e to the kt, that's perfect. And our general solution then on the right hand side, what does that look like? Right, what does that look like, Tyler?
Popcorn that one.
Popcorn?
Yeah.
Can I use P for popcorn?
Sure.
Popcorn is top. It's a next page in your activity. It says right at the top. General form is
M over 1 plus AB to the opposite KM.
yes, that's our logistic model. Good job, you guys. I'll go ahead and save this and upload it, and that key for the activities there. Check out that last one, number 17. What a whopper. Great job today, you guys. The OTL is on Moodle, but it's also right here.
Somebody